Okay. Do the things. I can hear you. You're just far from
you
your
can hear
mic.
me, but nobody was able to hear me because I had it muted from the last interview that I did. So
Okay.
now, and it has been madness, just absolute madness today. Now our audio levels are going to be totally whack, so you need to talk.
Maresy dotes and dozy dotes, a kiddly divey too, wouldn't you?
So I'm too low, you're too high. All right, let's bring you down. There we go. Try again.
Maresy dotes and dozy dotes, a kiddly divey too, wouldn't you?
So you're lower. You're still so loud. God, so loud, Pamela. All right, let's try now.
I don't mean to be.
It's fine. It's fine. All right, we should be similar loudness.
Okay. Okay.
And so you're going to have to tell us if we're all right. If we are okay. There we go. How are you doing?
I am cuddling my space heater.
It's really close to you there.
Yeah, we are anticipating about 25 centimeters of snow. That's roughly just under 10 inches, right around 10 inches to those of you who don't speak metric. And it hasn't started yet, but it's supposed to start any moment. And the problem with snow coming is not the snow. I'm down with the snow. The problem is I live in an old farmhouse, and this particular room in our house, the heater doesn't work. And
in that
when
one
it
room.
gets cold, yeah. So we have a few rooms in our house. Like the kitchen right now is colder than inside the fridge. So
Yep.
this is the smallest room in the house, and I'm heating it with a space heater, but it's like right here. Like if I sneeze or I too aggressively mouse, I'm gonna hit the heater.
We got a dump of snow just in the last couple of days, like probably this much. So 10 centimeters, maybe 12 centimeters.
Yeah.
And then it all quickly turned to rain. And so for one day, it's just the worst kind of misery. You know, no one had time to even clean off their sidewalks. So all the sidewalks are just mud puddle, or just like snow puddles. All of the drains are clogged up. So you've got this kind of rain mixed with snow in these lakes everywhere. And you just stay inside and you just go, nope. What's even worse is if you get like a freeze after that, and so then all of these weird shapes freeze, and now you can't go anywhere. You can't. It's the worst. So
yeah, we are anticipating 25 centimeters of snow, topped with half a centimeter of sleet and a glaze of freezing rain.
I should say hello to some people. Oh, go ahead.
Yeah.
Oh,
No,
I want to say hi to
gonna
Astro
say,
B, Bort Clankard, Camden Bassett, Dusty Reichwin, Giselle Sabrin, Gordon Dewis, Graham W, Guido Bibra, Harry Patrick, Holly Meyer, James Averson, Janelle Duncan, John Seffield, Johnny Zed, Kevin Ayers, Larry Beckham, Linda Sadek, Nancy Graziano, Paul from AstronomyNJ.com, Paul Gracie, Side MT, Susie Murph, Tad Awesome, Thomas Sepstrup, Umu, Uncle Bill Druin, Zapfan Zapfan. Sorry, if I don't say hi to people, then within a certain amount of time, then their names disappear, and then I don't get to be able to say hi to them. So, apologize for cutting you off there. That was super rude of me.
It's okay. I was blathering about death from the skies in the icy, watery format. I'm done now.
Gordon says it was minus 21 C out this morning. Feels like minus 33 with the wind. I don't think Fraser appreciates this winter weather. No, it's true. We almost hit freezing. It was awful. We almost died. Yeah, we live, as I've mentioned, we live in the Florida of Canada. So, what else is happening? Oh yeah, so go ahead.
There's a solar eclipse next weekend.
Do you mean a lunar one or both?
I meant a lunar one. Dang it. The
Yeah.
wrong word came out of my mouth. Yes.
Yes, lunar eclipse, and my plan is to live stream it again. So we learned a bunch of lessons on how to live stream an eclipse for the one that happened last summer that was visible in Europe and Africa. This one is going to be visible to North America. Dustin has generously offered to help out with gear from Oceanside Photon Telescope, so I'm hoping that we can do a really good eclipse live stream. So stay tuned.
That is awesome. I will be in Boston for the Eurasia Science Fiction and Fantasy Convention. So if you're in the Boston area, hey, come check it out. It's going to be at the Boston Park Plaza. And I will try and find internets. We'll see what happens.
All right, let's get on with this week's episode. For those of you who are wondering what it is that you've stumbled into, this is going to be a live episode of Astronomy Cast. We're going to record the episode and save it, and then stick around and answer your questions about space and or astronomy. Feel free to save up all your hard questions for Pamela. She likes the more challenging, the better.
He likes them. I simply answer them as best as I can.
All right, let me know when you are ready.
I think I'm ready. I'm pressing record. My levels look okay.
I have also pressed record. My levels, as always, are terrible.
I have to turn off my space heater. Crap.
But Chad is actually coming back to Canada, and he and I are going to spend a day just wrangling audio equipment. So hopefully we can make everything so much better.
Okay, so I'm going to muck with everything. I need to adjust my gain.
Okay, I'm going to turn off my audio recording, and I'll record again. You guys do this every week, yes?
Testing.
Yes.
Testing. Okay.
We do an episode on Friday at noon every week.
Okay, so I'm going to slowly freeze to death while we record.
Oh.
I'm ready to press record
All right.
again.
Okay.
I'm pressing record.
I have also pressed record.
Oh, the audio looks glorious now. It is glorious, and I shall be cold.
Oh, okay. Here we go. Astronomy Cast, episode 513, Stellar Fusion. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I want to take a moment to promote something that we are going to be at.
Yes, in Joshua Tree, or at least what's left of it.
What's left after? Apparently, they're cutting down. People are cutting down trees in Joshua Tree so that they can.
It's horrible.
Oh,
horrible.
Oh, this is just terrible. But yes, so Pamela, me, Paul Sutter, Skylius, John Michael Gaudier are going to be in Joshua Tree from June 26th to 30th for the All Stars party. And this is where we're going to be staying at this really fantastic resort. 4 nights, we are going to be setting up a whole bunch of really fancy telescopes. And it is going to be your personal star party with just us teaching the sky, taking requests, finding objects, doing astrophotography. Like, if you just want to be at the heart of super space nerdery, this is it. So if you want to find out more information, go to astrotours.co/allstars, and you can find out more about what it is, what it costs, and what we're planning to do. I think it's going to be a really fun experience if this is the kind of thing that you've ever wanted to do. And it's going to be fairly small, so it's going to be a fairly intimate time with cool telescopes. Yeah.
I will have hammocks.
Is that your plan? You're gonna hammock it up?
I'm gonna hammock it up, and that is the best way to do binocular sky, which is my favorite sky, and also the easiest to pack.
I think I am just going to be running around, moving telescopes in new directions and showing people what's up. It's going to be good.
That works.
All right. And now for the actual episode part, which I have lost. Hold on. Wait for it. Okay. There it is. Okay. The sun. It's a big ball of fire, right? Apparently not. In fact, what's going on inside of the sun took us some time and knowledge of physics to finally figure out. Stellar fusion. Let's talk about the different kinds of fusion and how we're trying to adapt it to generate power here on Earth. All right, Pamela. So the sun is not a ball of fire?
It's more like a ball of plasma.
And plasma isn't
It's
fire.
it's a thing. And I just want to say this episode is because I had a moment of, oh, I suddenly realized I totally don't understand something I thought I understood last week. During the Q&A that followed our live recording, we got to talking about brown dwarfs, what makes brown dwarfs, maybe stars, maybe planets, definitely confusing. And I brought up tritium burning, how they burn tritium. And someone's like, yeah, but tritium only has a half-life of like 10 point something years. And I became super confused. And I'm like, okay, I clearly need to do some research on this. And so this episode comes out of you guys totally stumping me, for which I'm grateful because now I know new things.
That's awesome. That is like the trick. Like I find that since I've been doing the YouTube channel and I've been answering questions, and I just get this, I get a lot of the same questions again and again and again. And every time that I don't know the answer to a question, I have to go and research the question. And now I get the answer. And if I make a mistake, then people slap my wrists on the YouTube channel. And so I just get better and better and better. I just get turned into this, I feel like I'm being honed in the fires of Mount Doom to answer space questions. And this is this exact process where you're just like, I want to know more about this thing that I kind of know a little bit about, but not enough to be able to explain it. So, so let's get into it. So where do you want to start? So, I mean, I think the first thing is just like, maybe some of the history, like how did we figure out what's going on inside the sun?
Well, it came down to realizing what it wasn't. In the 1800s, we had a whole lot of different scientists who were like, well, if the sun is made out of this highly combustible thing that burns very effectively and gives off energy, then it could only burn for this many thousands of years. Well, if it's made with this other thing, it can only burn for this many thousands of years. And no matter what they came up with, there seemed to be no legitimate way to have a sun that was giving off the amount of energy we have for as long as seemed sensible. And making it more confusing, this was about the same time that we started to understand that the fossil record was indicative of more than a few thousand years of Earth history, that dinosaurs might not have coexisted with humans. And we weren't really up on plate tectonics yet, but geologists were starting to get more and more indications that a 6,000 or an 8,000-year-old Earth was not what we were dealing with.
Right. You can't add up all the begats and get a proper age of the universe.
It does not work.
Right.
Now, this is the same time that we started to have quantum mechanics. And so we had folks like Beta that were looking at, well, what happens when you combine different atoms in different ways? And the answer was, well, in the right conditions, you have energy that is released. And then it becomes a question of what are the right conditions. And so they started out figuring out, okay, so if we put these two things together, what happens? And for a long time, they kept running into these issues of, well, expletive, this reaction doesn't seem like it's probable to happen because, well, it took a while to figure out quantum tunneling. It took a while to figure out all the little nuances of quantum mechanics that allows the improbable to actually happen in stars.
And so, for example, if you take two atoms of hydrogen, put them together, or four atoms of hydrogen, they don't just turn into helium. You need to put an enormous amount of energy into this process to make them, or pressure to make them do this thing. If you can, then you do get energy out of it, but it didn't seem possible.
Yeah. And it's even harder to try and figure out, like, how the heck do you get carbon and nitrogen and oxygen going in a cycle, because those helium atoms really don't seem to want to form carbon. And so it was figuring out all the tricks of the trickstery quantum mechanics that were necessary to make stars actually capable of having sustained, and the key word here is sustained, nuclear fusion in their cores.
So when did they really start to feel like they had a handle on that stars are doing fusion inside the core? They are mashing one kind of atom together to make another kind of atom and releasing energy in the process.
This started to come about in bits and pieces with Eddington and Beta and all of them working in the early 1900s. It took a while to fully work out all the pieces. And in fact, I think we're still working out some of the pieces. For instance, how the heck does a brown dwarf work? But it was really piece by piece figured out in the early 1900s. And one of the things that's fascinating to me personally is here we had Eddington was one of the major figures working in England, figuring out what it was that powered stars, how all of this nuclear fusion took place. And then Chandrasekhar sailed across the sea to seek an education with him. And in the process of that journey, Chandrasekhar figured out, okay, and after it's done burning, we can end up with white dwarfs that have a limit in their mass. And above that limit, they become a neutron star. And Eddington was like, that's too crazy. No, we're not. It's just like, how can one human being in one lifetime go from we have no idea how stars work to fusion to no, that's too crazy, we can't have electron degenerate pressure.
That's funny. So now what is the modern idea of what's going on inside a star?
Well, it all starts out with a collapsing blob of gas and dust, something that can be light years across, will collapse down due to whatever triggered reason supernova went off, shocked by hitting another cloud of material. And all of that diffuse material that may be thinner than the Earth's own atmosphere at the beginning will collapse and collapse and collapse until deep in the center of this proplid, this cocoon, this collapsing solar nebula, you start to reach the point where at the very center, the pressure is high enough and the temperature is high enough that you have atoms that are trying really hard to move around really fast. They're colliding with large amounts of energy. Because they're packed together, a lot of collisions are happening. This is why you need both the high pressure and the high temperature. The temperature says things are moving rapidly. The pressure says you're going to get a whole lot of collisions taking place. And at a certain point, deuterium fusion turns on. And this isn't at its beginnings the most effective way of generating energy. You end up with two atoms of hydrogen that each have a neutron attached to them. So deuterium, two particles, proton and neutron, bound up. That's deuterium. And when they collide, they create tritium, and they give off a neutron, and they give off a wee amount of energy.
So sorry, just like is deuterium for people who don't know?
So deuterium is that heavy hydrogen that is one proton and one neutron. So hydrogen, we like to come up with lots of special words for. Everyday run-of-the-mill hydrogen is just a proton and electron flying around having fun, or not.
Right. Going about their solemn business of creating the universe.
Exactly.
Yeah.
You add a neutron into that, and now you have deuterium. You add two neutrons into that, and now you have tritium. You have three particles.
Right. And sorry, hydrogen, once again, sorry, and deuterium and tritium are very rare compared to the amount of
regular hydrogen.
Regular old hydrogen.
And at the end of the day, ionized hydrogen is a proton.
Right.
So essentially we have three particles, a proton, an electron, and a neutron that we combine in various ways to get various words that all mean hydrogen in different states.
Right. And so I'm just kind of imagining now the core of this star where you've got this intense pressure. Most of the stuff that's in there is just a bunch of protons bumping into
Protons.
each other. Occasionally there's going to be these proton neutron pairs, and occasionally there's going to be these proton neutron neutron pairs, and they're all whacking into each other in there in the
And
core of the star.
the tritium don't occur naturally. They have a very short half-life, a little over 10 years. So you create a tritium and it's gonna go away. So this is where you have to start off with this deuterium burning, the nucleus that's a proton and a neutron plus another nucleus that's a proton and a neutron. You collide them together, it gives off a wee amount of energy, but in the process creates that tritium. And it's that tritium that opens the door for energy generation that really matters. Once you have tritium burning, which is where you take one deuterium, so a proton and a neutron, you take one tritium, which is a proton and two neutrons, you combine them together. This gives you helium, so you finally have a new atom. This gives you helium, this gives you a neutron, and this gives you 17.6 mega electron volts of energy. So this is a highly energetic reaction. Now you can do this reaction in slightly different ways. So you start burning deuterium and helium at this point because now you have helium and you can start releasing even more energy. And this is all referred to as the deuterium cycle, but it's that deuterium tritium combination that's most important. It is once the tritium's there, it occurs 40 times more frequently than just a straight old deuterium reaction. So you're going to have more frequent reactions and they give off more energy. So that's where you really start generating, well, generating that light that makes a star a star.
And that increased energy increases the temperature that's down in the core of the star,
Yes.
allowing the less likely protons to bounce into each other to give them a better environment, a better chance of being able to do their part.
And there you still also need the added mass. And this is where we start looking at what are the boundary conditions between a brown dwarf and a red dwarf. So if you have an object that is just a dozen-ish times the mass of Jupiter, there is theoretically the possibility that my dog just lost her mind. One moment, I must release the hound. Oh. Eddie opened the door for me. Okay, that was convenient. Sorry about that. Sorry, now there's a dog in the background.
Good dog.
Yes. Um, so what we were talking about last week was that boundary between the brown dwarfs and the red dwarfs, and that boundary is a function of what is able to burn. We have theoretical models that say at about the 12 Jupiter mass level, 13 Jupiter mass level, you're going to start to be able to get some of that deuterium burning. Not a lot, because there's not going to be a lot of deuterium. But while there's deuterium, it's going to burn. It's going to burn some of it into tritium. You're going to have that deuterium tritium burning taking place. It's going to give off energy. But at that level, you will never hit the energy, you will never hit that temperature pressure combination necessary for the regular everyday hydrogen, by which I mean protons, to start having fusion and having a prolonged nuclear reaction.
And so with the brown dwarf stars, they've still got the same elements in them that a regular star might have. They're going to have mostly hydrogen and helium left over from the Big Bang. They're going to have some flavor, some amount of deuterium. that deuterium is going to be able to fuse and produce tritium, and it's going to have those kinds of reactions, but it's not going to be able to get hot enough and high enough pressure enough to be able to turn the regular hydrogen into energy. And so it eventually just runs out of fuel in its core whenever it runs out of deuterium.
Yeah, and sometimes with some of the higher mass, we're not exactly sure how much higher mass brown dwarfs. You can also get lithium burning, lithium-7, when you hit it hard enough with a proton, which I mean an ionized hydrogen atom, you can end up with helium as an outcome. But lithium, again, is another one of those super scarce elements. So once the star has burned up all of its lithium, again, no more burning for you. So somewhere between 75 and 80 Jupiter masses, you can get more fusion, but you can't get sustained fusion.
Right. Okay, so then, I mean, so I guess you've answered your question from last week and how you sort of define that difference. So let's go back to the regular form of fusion as we understand it. The ones with the protons, once you've got that temperature, that pressure in the core, what is going on in the core with the atoms? What is the cycle that goes through for that?
Well, this is what we call the proton cycle. And I, for one, feel it is deeply wrong and annoying that they go from calling it tritium and deuterium to, when they get to actual hydrogen, suddenly they call it protons. Anyways, with the proton-proton cycle, what we have is two hydrogen atoms collide, form a deuterium. Then that deuterium and another hydrogen collide. They create helium-3, and they give off energy and a neutrino. And people get upset because we don't see the neutrinos in the correct numbers. But it turns out neutrinos have identity issues,
and they
change a lot. Yeah, so that's a different episode.
Yeah.
But it's solved. When I was a student, we hadn't solved that yet.
I think it had gotten solved during Astronomy Cast.
Yes.
Yeah.
Yes. So we got to discuss that early on. So we have this process where regular everyday hydrogens, by which I mean protons, come together, build up to the deuterium. The deuterium and the hydrogen build up to helium and neutrinos and give off energy. And this starts to get us then to the heliums combining to form helium-4, which is far too stable, but also more hydrogen.
No, is that helium-4 cycle happening in the sun right now?
Yes.
Okay. And so there's like a limit, right? There's sort of as much,
yeah.
I mean, as we mentioned, like a brown dwarf only has enough temperature and pressure to allow deuterium to form. What is the limit for what can happen in our sun in its current state?
So with our sun, what's going to happen while it's what we call a main sequence star is it's going to work on building that hydrogen up into helium over time. And as it builds up and ends up with more and more of that helium-4, eventually the helium-4 is just going to be like, and we're done now.
Right.
For a little while, light generation is going to stop, the star is going to collapse a bit, and then it's going to change state as it evolves.
And this is when it's starting to die.
Well, it's in this case, yeah, that's the correct phrase, as it's starting to die. So stars like our sun will spend the majority of their evolution with this proton-proton cycle going on in the core. Once they're done with that, once they have that helium-rich core, they still have some life left on them, but really they're starting to angle their way across the color magnitude diagram towards that great right-hand corner where they become planetary nebula. And at that point, they have added shells of material. So they've begun at one point or another burning a shell of hydrogen. They've done some helium burning. All these different phases are working towards that point where, depending on the mass, you can end up with either a helium white dwarf, a carbon white dwarf, and an atmosphere that drifts away to just form something really pretty for somebody else far across the galaxy to look at.
And in each one of these steps, right, you have this situation where the the waste is building up in the core of the star. In this case, say it's helium. The sun can't turn that waste helium into, it can't turn it into anything else, and so it just gives up and goes, well, I'm out. And so then the star starts to cool down, collapse down, because it no longer has that light pressure that's pushing outward. And then things get more and more concentrated, higher pressures, higher temperature. Goes, oh, wait a minute, I got this.
Now I can do
Now I
something
can do
else.
this, right? Now I can do this next thing. And then it not reignites necessarily, but heats back up, expands, gets much bigger, and then uses
Yeah.
up this waste and goes, okay, that's it. I promise this time, the last time, I'm done.
Yeah.
Now I'm going to shrink. Oh, wait a minute. I can do this. And it just, expands again and does it again until it runs out, till it's out of tricks.
And it all depends on the size of the star. Even on the main sequence, not all stars are the same. So while our star is happily doing this proton chain, there are other stars that are higher mass than us that are sitting on the main sequence doing what we call the Cno cycle, the carbon, nitrogen, oxygen cycle. And in this particular situation, they're combining hydrogen atoms, they're combining positrons, they're getting to helium rather rapidly. And as they go through the cycle, they're building themselves up to heavier elements, but it's still a main sequence star.
So how big a star do you need? Like, how much more massive than our sun do you need to be able to have one that uses this different cycle? It's the Cno cycle, right?
It's the Cno cycle, and you only need to be about 1.5, not quite one and a half times the mass of the sun. So it's just a little bit bigger,
Right?
Not a lot bigger. But when you look at the fact that the majority of the stars in the universe are smaller than our sun, it's really something that not a lot of stars do. So when we teach our students, oh yeah, it's all just burning hydrogen, it's an oversimplification, but it works for the majority of the stars.
And so will you get like both going on at the same time, like a much more massive star than our sun? It's going to have the proton fusion going on,
Exactly,
as well as the Cno cycle, as well as deuterium burning. Like, whatever is possible will be happening inside that core
in
different ratios. And will you get and this sort of question just came up in the comments, and I just wanted to throw this in as well. Will you get different kinds of fusion in different layers at the same time of the star, depending on how massive it is?
Yes, once it moves off the main sequence. So during the main sequence, in those slightly larger stars, you're going to have those hydrogens coming together, getting you to the helium, which allows you to get to the carbon and starts the Cno cycle on. Now, as stars evolve, you will initially end up with the core gets filled up. And when that occurs, you can have a shell of hydrogen that begins burning around it. As that core of hydrogen burns, the helium core beneath it, as that shell of hydrogen burns, the core of helium beneath it will get more massive, will get heated up, will eventually light up and begin helium fusion. Now, eventually, if the star is big enough, when you have burned up that entire helium core, you're going to keep expanding out. You're going to keep getting more different kinds of materials. From that, you end up with a carbon fusing core. That will fill up. From there, you end up with neon. Eventually, you'll end up, well, if you have a star that is 8 times the mass of our sun, you can end up burning all the way through, so that your layers are, the outermost layer is a shell burning hydrogen, that it sits atop a shell burning helium, that sits atop a shell burning carbon, that sits atop a shell burning neon, that sits atop a shell burning oxygen, that sits atop a shell burning silicon, which is getting fused into iron.
Right.
And when all of that silicon fusion creates an iron core, well, the thing with iron is everything up until you get to iron releases energy during the fusion process. But if you want to fuse a couple of iron atoms, they are going to demand you give them energy. And that giving the energy is kind of the opposite of how stars work on the insides.
Right.
So
And
that's when supernovae occur.
right, and this is when it all and this that process. I mean, those heaviest, the silicon going into iron, these all happen incredibly quickly.
Yeah, just millions of years. It's one of these things where, because you have so massive a system and you have stuff that is burning at higher temperatures, you have extraordinarily rapid fusion going on. It is burning through its significantly larger amount of fuel very, very quickly. And it they die and go boom.
Yeah.
And for this, we are grateful, because this is where all of our heavy elements that got freely released to create stars like our sun that are capable of having planets. This is how all of that happens.
Yeah. Yeah. So we kind of need it.
Yeah.
Um, and then what? What happens to those? For the smaller stars where they can't support the fusion anymore, up to the ones that go supernova, like in that sort of you know
Well,
0.13 to 7.5 times the mass of the sun. What do you get?
there's basically four fates across the entire spectrum to broaden it all the way out. Those brown dwarfs, they're going to burn their deuterium. The bigger ones are going to burn their lithium. And then they're going to sit there going, I was maybe a star.
I'm
Hi,
out.
I look like Jupiter now. So they're just going to be sad and pathetic. The red dwarf stars, the extraordinarily low mass objects that are in the hundreds of Jupiter size, but tiny, they are actually going to be capable of fully burning their entire atmosphere in this proton proton process. They are convecting like a little tiny lava, well, like a giant lava lamp star, where material in the center is broiling up to the surface, roiling up to the surface, and they'll burn that proton proton cycle for trillions of years. As you get to stars like our sun, after about 5-6 billion years, they're like, and we're done with this proton proton cycle. We're out. We're going to start the rest of our
Yep.
evolution. And they end as white dwarfs. They end with those planetary nebulas. And this is what you get up until you start getting around the 8 solar mass mark. At the 8 solar mass mark, this is where things start going boom, because they have formed an iron core. Now, exactly how much they go boom, how they go boom, is going to depend on mass loss rates. And here's where things start to get messy, because the mass that a star starts with is not the mass that a star ends with. You could conceivably have something that starts out as 4 solar masses and ends up quite happily being a white dwarf because it's lost enough mass. Then you could have something that started out as a few hundred solar masses and ends up as like 10 solar mass black hole. Solar wind and mass loss is a real issue. We still don't fully understand it. We don't know how much mass is going to be lost. All we know is if you die at a certain size, you can go boom.
Right, right. And sometimes you end up as a neutron star. Sometimes you end up as a black hole. Sometimes you end up as nothing.
Nothing.
It just goes kaboom and it's all gone. So, well, that was awesome, Pamela. I'm really glad we got the question last week, and that took you the time to go into great detail. And now we will all remember forever. So thank you.
That tritium decays and is made by merging deuterium.
Awesome. There you go. See you next week.
See ya. Bye bye. And now we save.
513.
Yep. I have a really large monitor for which I am very, very grateful, but some corners of it are just on the edge of what I can read.
Is it a new monitor?
Yeah. Well, it's new enough.
I just have
I
4
got
monitors, and I want 2 more. I want 6.
so I have a 43-inch diagonal. I got this September, so it was shortly before I found out I was going to lose my job, or lose the funding. I have a job.
Right.
I have no paycheck.
You sound like a
This is one
government
of those.
employee.
This is one of those things they don't tell you is an option when you're in graduate school. So I have a great new job
Yeah.
and no paycheck to go with it.
Well, welcome to being
Um,
an entrepreneur. That is always an option when you run your own business.
I know. Yeah, yeah. So I got this before I realized that was going to happen. It's a 43-inch diagonal. It's kind of sweet. I normally will stick like YouTube videos and stuff up in the parts of the screen that I can't read as easily. But today I stuck Audacity up there.
All right, we got some questions.
Okay.
So Paul from astronomynj.com asks, does any of the iron fuse at all? So when you end up with that end, no.
No, you can end up, fuse is the wrong word. You can end up with things like neutron bombardment particles where neutrons bombard the iron atoms, and you can end up with slow processes or during supernova rapid process elements forming, but it's not fusion.
Right.
It's let's pile neutrons on until you feel the need to decay into something more interesting.
Right. So it's this situation like when the outer layers are collapsing and the star is imploding and it's coming in at 70% the speed of light. I forget, as the whole thing is just going and imploding.
Yeah.
That
It's having a bad day.
That's when you get those heavier elements, but it's not because they are being fused in that they're being squished, but not in the regular fusion processes.
And to give everyone a sense of scale, these 8 solar mass stars are roughly the same size as Jupiter's orbit.
Yeah.
So these are massive systems, and then they collapse down in some cases to like the size of Manhattan Island when they become neutron stars. Now, there's a lot of mass lost in the process, but still, this is a dramatic collapse.
Yep. Arjun asks, so red dwarfs and brown dwarfs do not add any elements to the stellar medium, but the exploding ones led to future heavy metal stars and planets. Yeah, so are red dwarfs and brown dwarfs just greedily hanging on to all of their elements forever?
Yes. Well, red dwarfs can have mass loss through stellar winds, through flares, which they like to do. But when they have mass loss, it's the same kind of mass loss our sun has. And it gives off material, sure. It just doesn't give it off as effectively as a supernova is going to do.
Right. Paul Gracie asks, can a star really decay into nothing, or does it decay into something that we can no longer observe?
It's not that it decays, it's that it explodes and distributes its material in all directions. Think of it as you can either pop a balloon and end up with a former balloon in your hand that is all one piece, or you can fill it with some sort of an explosive gas, ignite it, and have shards of balloon fly in all different directions, and that myriad of pieces is no longer a balloon.
Right, but the balloon is still there. It's just in pieces of shrapnel flying through the air.
So when you're left with a neutron star, that's sort of like the balloon that has nothing left in it, but squished a whole lot. And when you're left with nothing behind, that's when you have the shards of the balloon in all directions.
Yeah. And this is still a bit of a question, because astronomers have been finding these, they call them unnovas, where a supernova should happen, but the thing just winks out into a black hole in a moment.
Yeah, we're still figuring these things out. And And just as a reminder, yes, heavy elements are formed. Otherwise, we wouldn't have gold and silver. They're just not formed during nuclear reactions in the centers of stars. They can sometimes get formed during neutron bombardment processes in the outer layers of a star. They get formed during supernovae. They get formed during neutron star coalescence. They get formed in a myriad of ways that just aren't nuclear fusion in the core of the star.
Yeah, and this was one of the exciting discoveries with the gravitational wave discovery now a year and a half ago, where you had the two neutron stars collide into each other, and they detected gold in the wreckage from this explosion. And so you can see that, and I've heard everywhere from, like, 2 years ago, if you said, where does this come from, you would have said they come from, gold comes from supernovae.
I have said that.
You probably have, yes. And now,
on this show,
right? And now the thinking is gold seems to come from maybe supernova explosions, and for sure neutron star collisions, and maybe not supernova explosions at all. Like, maybe the supernova, they just hang on to it all. And so it doesn't get released from the supernova at all. And
it's awesome.
Yeah, and all those heavier elements could have come from colliding neutron stars, which is a mind-bending concept. John Drake asks, why does it take so long for photons to go from the center of the sun to the surface?
Because they get lost. To put it more mathematically, there's what's called Brownian motion, or as they explain it in college, because they assume this will work, they drunk walk out of the center of
random
the sun.
walk.
Yeah, and it's a matter of, imagine trying to get out of a football stadium, by which I'm actually thinking European soccer stadium, with your eyes closed, having just finished drinking however much the average attendee from a Northern European country drinks. And as you go, every time you bump into somebody, you get spun around 5 times, but you don't know if it was 4.5 or 4.25 or 5.5. You just get spun a bunch of times, and then you start walking again. This is not going to be an effective way to try and exit the stadium.
Yeah, and so you can imagine, right? Each photon goes into a atom of hydrogen and then gets re-emitted in a random direction, and then it happens again, and you have to get hundreds of thousands of kilometers from the inside of the sun to the outside, and it can take 50,000, 100,000 years.
And it's that radiative internal part of the sun where everything gets slowed down so much.
I'm sure the occasional one makes the journey really quickly. They just,
statistically, yeah. And statistically, there are some that are just like, F it, I'm staying here forever.
Yeah. There could very well be in there some photons that have never made it out in the history of the sun.
And it's not a specific photon that does that. It's the energy of a specific photon that's getting absorbed and re-emitted and absorbed and re-emitted.
Right.
So every time the energy gets absorbed, the photon dies. Every time it's re-emitted, it's like resurrection, but it's actually a new photon.
Right. All right, next question. Paul Nash is asking.
It's starting to snow, so we have a hard stop in 10 minutes because we have to go get our car at the automotive place.
Okay. Arjun is asking, how much of a star is turned into energy via E equals mc squared?
So this is horrible. We don't actually ever think of it as E equals mc squared. What we think of it as, you hit these two things together, they stick together to form something new. The binding energy of that new thing is less than the binding energy of the two previous things, and that difference in binding energy is what gets released. And that's just how we think about it. In general, the number of particles is conserved, or while particles may change, we just don't think of it in terms of E equals mc squared. We think of it as, you have a hydrogen that is held together with this much energy required, and now you have this deuterium that's held together with this lesser amount of energy required.
Right.
So it's loss of binding energy. And I've never put it in those words
Right.
before, but really that's pretty
Yeah,
much
I
what's
mean, you
happening.
only get to approach E equals mc squared when you combine matter and antimatter.
Yeah.
Everything
Or
else
I
uses.
fission
Sure.
somewhat.
Yeah, but even that, I mean, from what I understand,
Yeah.
like the fusion in the sun is actually tremendously inefficient. It's just
Yeah.
that there's a lot of it going on.
And
But
a lot of things that are going from a highly bound state to a less bound state. Okay.
Jan Dryak or Yan Dryak? You have to tell me which one it is. It would be Yan. Okay, Yan Dryak is saying, is there an upper limit for the proton number, i.e., the heaviest element?
Yes. And the upper limit comes from how far the strong force is able to reach across the nucleus of an atom. The strong force only works over tiny, tiny distances. And if your atom is bigger than that distance, it's like, yeah, no,
Just falls
that
apart again.
proton's on its own.
Yeah.
And we are capable of building temporary atomic core that things are like, okay, trying to reach out in all
Yeah.
directions, trying to hold on, and it will fall apart quickly, but we can temporarily build larger atoms. But we've really hit the physical limitations. There's some thoughts that there might be an island of stability heavier up. I have to admit, I don't understand the physics of how you end
Right.
up with that second island of stability, and we've found nothing in it yet.
Right. And of course, we've had this conversation a couple of times now in the past, this idea that the most powerful particle accelerators, matter squishers that exist in nature are these supernovae. And so nothing that we can generate here on Earth will hold a candle to what a star collapsing at a significant fraction of the speed of light will be able to do. And the best that the universe has been able to provide naturally appears to be whatever are the heavier elements at the high end um, of the of the periodic table of elements. All of the other stuff happen, and they probably happen for short periods of time in supernova explosions as well. There's probably
Yeah.
atoms with 10,000 protons altogether. They just fall apart in a
I'm not sure you call
quadrillionth
that
of a
an
second.
atom or like some sort of a special condensate.
Yeah, yeah, yeah. And so, you can sort of imagine, I don't know, like if you're going to build a tower of oranges, right? And there's like a certain
Yeah.
size that will naturally be able to hold. And beyond that, you're going to have to be there holding it to keep that tower going. And as soon as you
Yeah.
walk away, then your
No
tower
more.
falls down. Yeah. Arjun is asking, could elements be made and distributed by active galactic nuclei? So could that be
Oh yeah.
another way
Yeah.
that those
Yeah.
materials getting
That
out? Yeah.
that happens. We just don't generally talk about it. I don't know how far up the um nuclear fusion they get. Uh I'm pretty sure that they hang out at more like the proton cycle kinds of stuff. But this is me working from a very old memory here. But the
Right.
reason they glow is they have fusion going on.
Yeah. Yeah. Yeah, I mean, we've talked about that a bit. That in the accretion disk around supermassive black holes, you've essentially got stellar fusion going on. It's so hot
The
and under such
details are
pressure,
different, but it's still the right temperature and pressure.
right? And you've got these enormous solar winds, these weird magnetic fields, these
Yeah.
jets that are blasting out halfway across the universe.
Yeah.
So it gets up to all kinds of wacky shenanigans. We got about 2 more minutes, and then we should probably shut things down so that you can safely get your car.
Yeah, and I there's some chat going on in the weekly space hangout about how no, it must be E equals MC squared. And really, most of the reactions, if you look to see how many particles you have on both sides of the equation, it's the same number of particles. They're just configured differently. And the energy comes from that change in configuration for the most part.
Right.
Um,
All right.
Yeah.
Well, why don't we wrap things up? I'm starting to feel a little anxious about your weather.
Yeah.
Uh,
It's already starting to stick
yeah.
since I
Yeah.
mentioned it to you.
Yeah. And but before we do, I'd like to give a big thanks, as always, to our good friends at the Weekly Space Hangout crew. They are the producers, they are the fans, they are the co-creators of everything that we do. And if you want to be a part of that community, go to wshcrew.space, and they will give you everything you need to know to be able to join that amazing community, especially now as Google Plus is shutting down the communities, including the place where they originally formed. So now is the time. Make sure you go and join the Weekly Space Hangout crew.
And I just want to add to that we recently did a massive upgrade to the astronomycast.com website. And I was having a day. I was just having a day because
Thank you,
I,
Pamela, and good work.
well, so I have to give a shout out, especially to Keeper of Maps. Oh my gosh, he figured out how to hack into a server we no longer had the keys to because it was built by someone that we're no longer working with. Um, and yeah, I didn't even know you could do some of the things
Yeah.
that he did. And a whole bunch of different people have come in and helped us add in featured images and helped
Yeah.
us fix the formatting. Our website would not be as solid and as shiny as it is without the work of so many amazing volunteers from the Weekly Space Hangout crew. So thank you. I
Yeah.
got to sleep because of you.
And so, if you're feeling like you have lots to give and you're just watching astronomy, listening to Astronomy Cast, watching it home alone, get involved in the community.
Yeah.
Be a part of it. It's fun. They're great people. We couldn't do this without them. All right, let's wrap things up. Thanks, everyone, for watching. We will see you all next week.
Sounds great, Fraser. Bye-bye.